In this lecture, we're going to begin looking at applications of Maxwell's equations. In particular, we're going to be looking at applications of electromagnetic induction. To begin, this table summarizes Maxwell's equations as we know them now and as they have been updated using the results of the previous lectures. So let's go through each of these one by one. The first equation here is Gauss's law. It says that if we take the surface integral d dot ds, then the result of that must be the charge enclosed in S. Note that the surface integral here is being shown as a single integral, but it should be understood that that means a double integral. In point form, we know that the divergence of d must be equal to the charge density at that point. So both of these equations say the same thing. One is a macroscopic relation, the integral form. One is a microscopic relation in point form. And the point form equation basically tells us that d fields always possess a non-zero divergence if there are charges present. And we know that case to be true for the electric and electric flux density fields. The second equation in the second row here could be thought of as Gauss's law, but is applied to the magnetic flux density field. So this says that if we surround any sort of source of magnetic fields by a closed surface S and integrate B dot ds, the result will add up to be 0. In the microscopic or point form, that means that B cannot have a divergence. That is, there's no such thing as a magnetic monopole or a magnetic charge. You only ever find magnetic dipoles, a north pole and a south pole, for example, coexisting together to produce a B field that does not have any divergence and has to have a circulation. The third equation is Faraday's law. So we have updated the original form of this equation. Previously, for electrostatic fields, the right-hand side was 0, but for electromagnetic fields or time-varying fields, this is no longer the case, and the result is actually minus d phi by dt, where here phi has been computed by taking explicitly the surface integral of b dot ds. The corresponding curl equation on the right shows that if we have a time-varying B field, then the electric field is actually allowed to have a circulation. So again, in electrostatics, the right-hand side was 0, but in a time-varying case, we are allowed to have a circulation in E. Ampere's law is the fourth row of the equation. Again, this part of the equation is what we understood to be Ampere's law previously, but we've seen that in addition to the conduction current I of T, we've had to add a displacement current given by the surface integral of the partial derivative of d with respect to time, which is the displacement current density. In microscopic or differential form, this means that the curl of H is contributed not only by the conduction current density, but also by the displacement current density. And we found this last equation by actually using an auxiliary equation, an additional equation, which was the equation of continuity. That's not one of Maxwell's equations, but we've just listed it here because it was integral to finding the Ampere-Maxwell law. So this says that if we take a closed surface and integrate the current density passing through it, then the result of that must be the time rate decrease of the charge enclosed within that surface. And this was discussed in the equation of continuity lecture. In point form, it says that J can have a divergence. Sorry, this is needs to be corrected here. Divergence of J is equal to the partial derivative of rho v by dt. There should be a minus sign here as well. We also have auxiliary equations. These auxiliary equations are supplemental equations that link some of the field quantities that we see in the previous slide. So one of those is the D field, which is related to the E field through a parameter epsilon, the permittivity of the medium. We also know that the magnetic flux density B is related to the magnetic field H through permeability, mu. And we know that conduction current density is related to electric field through a third parameter, sigma. So, or electrical conductivity. So these three parameters define the medium in which we are measuring these fields. So in effect, we really only have a limited number of unknown fields appearing in Maxwell's equations because these quantities are interrelated as shown by the constitutive relations. We can also relate conduction current density to the volumetric charge density through this velocity equation that you see here. If we think back to currents, we define J as related to the velocity of a charge or charges within a charge distribution rho sub V through this relation here. And whether that current was a result of a conduction current or a convection current, which doesn't require conductors to flow, that still leads to a current density, and the same underlying relation can be used to find that. As our first example of applying Faraday's law of electromagnetic induction, let's consider an electromagnetic ring launcher. A video of this was posted on the EC221 website on YouTube, and I would like to encourage you to watch that video first before we proceed with the analysis in this slide. So in the video, they have a coil of wire that's been wrapped around magnetic core material, like what you see here, and then a conducting ring is placed over top of it, and you see that copper ring or conductive ring placed here. So I want to emphasize that that ring is a closed ring. There's no gap in that ring. It is a continuous ring that conducts current and is placed over top. So let's proceed and analyze what happens in this particular situation. So here we have an AC voltage source, and in the video, this coil was plugged into the wall via a switch. So let's pretend that this is a sinusoidal voltage source that is connected to this coil. And in particular, we're going to be concerned with the current that flows into the coil, because that's responsible for creating the B field that will be generated by this coil. So let's consider first of all a plot of the current that is going to flow in this circuit. So let's label our current here I of t. And it will begin to flow once the switch that we see located here is closed at some certain time. So let's plot I of t here as a function of time, and at time equals 0, let's say that the switch is closed. And let's say that I of t is a sinusoidal alternating current type of waveform. Now for the analysis, we need to look at the magnetic flux density, or more specifically, how the magnetic flux or the magnetic flux density changes with time. So for the time being, let's pretend that we are at some point here. Let's call it T naught. I've chosen this point just so that we can see that the current is increasing with time at this particular point. And we can consider other points of time later, but let's first look at what's going on at this point in time. So at this point in time, the current is increasing and it's a positive value. So that current is going to flow through the windings as we see here. So we know that each of these windings acts as a loop, and using our right-hand rule, we can actually determine the direction that the B field is generated. So let's sketch the B field here in a different color. We know that the B field is going to be generated within the core and enter from the left and leave from the right. Something like this. The B field will look like this. And it's a time-varying B field because the B field is related to the current, is proportional to the current. So if you wish, you can think of the sinusoidal curve as also that associated with the B field. Maybe it has a different value, but this could be seen of as a plot of B of t, or more specifically, some component of B of t, which we haven't specified here. So at that same instant in time that we were looking at for the current, B is also an increasing function of time. That's important because we need to integrate B over the cross-sectional area of this coil to ultimately get the flux. Okay, so the flux is principally generated over the cross-section of this coil, especially if the material comprising the core is magnetic, that has a large permeability. So that flux will be generated over this area, over S, and we know that flux in general is arrived at by doing a surface integral of B dot ds over that area. Then when we apply Faraday's law, we're going to have a look at the electromotive force that is induced into that ring that is placed over top. So we know that Faraday's law says that the EMF produced must be minus d phi by dt, and since our ring only comprises a single turn, it suffices for us to use phi and not lambda in this expression. So that electromotive force induces an EMF in the ring, and that is going to motivate a current to flow in that ring. And because of Lenz's law, essentially the minus sign that we see here, the current in that ring is going to flow in a direction such that the B field produced by the ring because of that current would oppose the magnetic flux that is passing through it already. So that means that the current in this ring needs to flow in this direction. We'll call this the induced current. And notice that analyzing that ring by itself, if we had a current flowing in that direction, the magnetic flux produced by that ring would flow in this direction to counteract the increase in B that we see happening at this point in time. So remember, this snapshot is for the particular point in time where B is increasing, and so this current is going to flow in the direction shown and produce its own induced B field, which opposes the red B field that was present there. So this is I, the induced current. Now we want to try to rationalize why the ring gets launched off of the end of this ring launcher. And actually, it's not possible for us to completely rationalize that with what we have so far. To see that, let's consider a top view of the ring. So let's pretend that we are looking at the ring launcher from over here, and let's look down the axis of this ring launcher. So we will see the ring, which I'll draw as a circle here. So looking down, here's the conducting ring. And since we're looking down that axis, this ring has a current that's pointed in the direction shown here. And the B field, or the magnetic flux density, is coming out of the page and is confined to the interior of the ring. Okay, so if we consider a single point charge on this ring, a positive charge, and it's moving with some velocity in this direction, the magnetic force on this is IL crossed with B, and we'll attach the direction to L here. So L, in this particular direction, we can see that L is in the phi direction because it's rotating around the central axis of the ring. So we could say that this is going to be I proportional, let's say, to I phi hat, and B is in the Z direction, if we assume that the Z direction is along the axis of the ring launcher. And this cross product of phi and Z would result in the radial direction, right? And that doesn't make any sense because that means that this this ring is going to be pulled in the radial direction. In fact, if we cross the direction of the current that we see here with the B field, so we actually compute the direction of IL cross B, that's going to be in the outward radial direction. So this charge is going to feel an outward radial force like this. And that would be true of every other point on this ring. It would experience an outward radial force. And so the ring is going to want to be pulled apart by this B field, but that certainly doesn't explain why the ring actually moves in the Z direction. And just to be clear, this is the Z direction that we're talking about here. So apparently we need a little bit more information to describe what is happening here. What's actually happening is there's nothing wrong with the picture that we've drawn here, but what is actually responsible for the ring being launched along the longitudinal direction is the fact that the B field actually extends outside of the solenoid, outside of the region that we've sketched here. To make this a bit clearer, let's consider a side view of this problem. So here is our ferromagnetic material. Here is the Z direction, and if we were to draw our ring, here's our ring here being wrapped around, and if the B field is in this direction to match our diagram, maybe I'll draw this in red since we did this in red previously. So the B field is flowing in this direction, we'll call this B, then that results in the induced current, which to match our diagram should flow like this. So this is the induced current. So to explain why the ring, that there's going to be a vertical force on this ring, we actually need to look at the B field outside of the core material. So let's complete our sketch here. And what's going to happen outside the core is that these B fields have to form closed loops. And this looks very much like a magnetic dipole, right? With this B field coming about like so. And there's significant curvature to this B field. It's not just simply in the vertical direction. So if we were to decompose B, and let's try to exaggerate this on, let's say, one of these curves. So let's make this a very curvy B field here. So if we were to look at the B field, let's say at a particular point, let's say over here, we can see that there are actually two components of the B field, one in the Z direction and one in the radial direction, which we'll call BR. Okay, and it's actually this radial component of the B field that is responsible for the vertical force. So let's redraw this diagram that we have up above here. So let's draw our ring from the top view, which looks like this. We established that the current is flowing in this clockwise direction. And now let's draw the radial B field around the outside. So we have a radial B field that has some components like this outside of the solenoid, which are called BR. And then I is in the phi direction, or the current is flowing in the phi direction. Well, now, if we consider a cross product of a current that's in the phi direction and a B field that is in the radial direction, we're going to get, using the right-hand rule, phi, which is, we could choose any direction here. Let's say we're considered with evaluating the force at this point. So if we take the current and we cross it with the radial direction, that's coming out of the page, right? We're going to see a force, which I will draw here in blue, that's going to come out of the page, which is our magnetic force. So this is in the Z direction. Okay, so we're not going to work out the actual magnitude of the force here. The point is to show us that it's the radial B field in the vicinity of this ring launcher combined with an induced current that flows in the azimuth direction that leads to a longitudinal or Z-directed force on the ring. And that's what leads to the ring being launched in our ring launcher video. So one thing to note in this example is that this process also holds at other points in the time cycle. So I was careful to point out at the beginning that for simplicity, we chose a point on the graph on the right where B of t happened to be increasing in time. That way we could easily work out the direction of the induced current and the direction of the force on that ring. Well, actually the same argument can be applied regardless of where we are at different points in time. If we happen to be on a different point of time here, for example, when the B field is negative and decreasing, you would just draw all the arrows that we sketch on this diagram in the exact opposite direction. But it turns out that if you evaluate that cross product, the force will still be in the positive Z direction. And so that's why we were able to use alternating current in this ring launcher and in the video that you saw, because at every point along this time curve, the force generated on that ring is always in the positive Z direction. And it would be a good homework assignment for you to trace out what's happening at other points in time on this curve. As another example of electromagnetic induction, I'll point you towards an induction stove. So if you look at the middle panel here, this photograph shows a modern induction stove where we take a metal pan, and it's important that that pan has a high permeability. So we usually use iron pans or pans that have a significant ferromagnetic component in them. We can't use, for example, copper pans or aluminum pans for this, and anyone that's familiar with induction cookware might be aware of the fact that it's made up of principally iron. So we place this iron pan on top of a glass surface. The glass isn't important here, but below that glass is basically a coil of wire. And that coil of wire is just a number of turns of copper wire here. And that pan is essentially acting as the core material. The difference is that the core is not within the wire windings, but just right on top of the wire windings. But the effect is the same. What's going to happen with this coil that we see on the right is that if we have a current that's circulating around the coil like this, that's going to produce a B field that points out of the page. And let's consider what happens if we were to put a ferromagnetic material on top of that. So if we imagine our coil on the side and then we place our pan here, this pan has got some thickness to it, and now we're exposing that pan to a B field. Well, that is shown over here. Imagine now the B field is coming out of the page and you're looking at a piece of that pan facing you. We know that that pan is made up of a conductive material. So if I have a B field passing through that conductive material, for any closed path that I can imagine, I can develop an EMF about that closed path and make a current flow. So shown in this diagram here are a bunch of closed paths around which a current can be induced, because this is within our pan material. This B field is passing through, so I induce these circulating currents within the pan itself. And these are called eddy currents. And because the pan is made up of a resistive material, anytime I have a current flowing through a resistive material, it produces heat. And the amount of heat is equal to the power dissipated by the pan. That's I squared R, right? So if I know the resistance of the pan and I know the amount of current that's been induced in the pan, I, because of this eddy current effect, this induction effect, I can work out I squared R and work out how much power is being thermal power is being generated by this process to cook food. So what's amazing about induction stoves is that they only work when you place this inductive cookware on top of them. That heat is entirely generated by the pan itself. It's very different from a convection stove where you have a heating element and you place a pan on top and it's just convection, heat transfer between the heating element and the pan that is responsible for heating your food. That's a very inefficient heating mechanism because a lot of heat is lost to the surroundings. Here, assuming 100% efficiency of the coil, you're using that magnetic field to couple into eddy currents exclusively in the pan. So the pan is used as the heat generating device. And this is very efficient and also leads to localized heating of the pan itself. And you can see this in the photograph where we have a piece of chocolate on the pan and it's melting on the pan, but sitting on the glass surface, the glass doesn't get hot at all because there are no eddy currents induced in the glass. It's a perfect conductor. That glass remains basically cool to the touch. Of course, the glass will heat up over time just because of heat transfer from the pot, but you get the idea. So these eddy currents are actually being capitalized upon in this particular example, but they can also be a tremendous source of loss. You'll recall that when we had a transformer, that was basically a ferromagnetic core over which we wrapped a bunch of wires on to form a primary and a bunch of wires to form a secondary. It's a very crude drawing, but we are essentially doing the same thing here, right? We are trying to create a B field in that transformer core in order to produce a magnetic flux that travels in that core and couples to the secondary coil. Well, because that core is made up of a conductive material, if we subject that core to a B field, we will also induce eddy currents to flow. So if we were to look at a cross-section of that core and look at it like this, that B field, which is, let's say, coming out of the page, is also going to induce eddy currents to flow inside of our core material, and our transformer is going to heat up. And we don't want our transformer to heat up. It's not designed to be a heating device. In fact, the heat might eventually cause the transformer to be damaged. Our goal is actually to get 100% of the power coupled from one winding to the other and to have no heating losses within the transformer itself. So we want to minimize these eddy current losses in the transformer. And so what we find in the transformer to manage these eddy current losses is these laminated cores are used. So you actually take a bunch of sheets of metal and you pile them together as shown here, and actually you put insulators between the sheets. And so what that causes is that the area of the induced current, or the area of the loop, is much, much smaller. So now the current that can be induced in that loop is not nearly as high as it could be if you did not have these laminations present. So you're dramatically reducing the amount of eddy currents and hence the heating of the transformer core. So these are two effects that are on opposite ends of a scale in terms of wanting to take advantage of eddy currents. On the stove example, we're using the eddy currents to produce useful heat for cooking. In the transformer example, we're actually trying to minimize the eddy currents so that we can use the bulk of the power to facilitate power transfer from the primary to the secondary, or vice versa. So this is another very interesting example of electromagnetic induction.